All righty, problem numero 29. Here we go. It says in the figure. Oh yes, this is a good one too. Sorry about that. That sounded weird. In the figure, a solid brass ball with a mass of 0.28 grams. Seriously? 0.28 grams? Ugh. Hopefully we won't need the mass because I don't want to deal with that in kilograms. All right, it's going to roll smoothly along a loop-the-loop track when released from rest along the straight section. So the drawing it gives you is this. And so it tells you that this distance here is h. You're told that the loop has a radius of capital R. This point over here, horizontal from the center of the loop, is called point Q. So there's our drawing. So there's our little sketch. All right, what else do we know? It's going to roll smoothly along the loop-the-loop track when released from rest along the straight section up at the top. So let's call the top of that point A. So at point A, here are the things I know. The velocity is 0, and the height is h. Let's see, the circular loop has a radius of 0.14 meters. I keep losing my problem. And the ball has a very, very small radius. I don't know if you guys have ever seen this notation, you guys, in math class. But when you use two either greater than or less than symbols next to each other, that's math speak for this thing is so much smaller than this thing that it doesn't matter. Cool? And I wrote that there in parentheses just in case you hadn't seen it before. This notation indicates R is much less than R. Cool? All right. So A says, what is H if the ball is on the verge of leaving the track when it reaches the top of the loop? All right, so this is huge, you guys. You absolutely have to know how to do these types of problems. I would be very surprised if there wasn't something along these lines on the test somewhere. Okay? So we're talking about going around the top of a loop. Okay? At the point when it's just about to leave the track, what is true? Your net force isn't 0. Something else is 0.
The
normal force is 0, which means that all of my centripetal force is provided by force of gravity, right? So at the point at which you're on the verge of leaving the track, your centripetal force equals your force of gravity. Okay? That is huge. You absolutely need to know that for the AP test. And for life. Not really for life, but you could probably survive without knowing that. But anyway, there we go. All right. So I feel like we can find our V, right? That means that V is just going to be the square root of GR, isn't it? Okay, cool. So that is that. All right. I lost the problem again. All right. So let's call the top point of this loop where it's about to leave the track, let's call that point B. So at point B, we've just discovered that our velocity is the square root of GR, right? What's our height at that point? Oh, shoot, I can't use. Darn it. Okay, yeah, I guess we'll have to use capital H or something. That's annoying. So the height at that point is 2r, right? Oh, shoot. What did I do wrong? I did a thing wrong.
I have no idea. Everything gets so far.
What's the radius of the circle that the ball is going around? Capital R. Good? All right, so do you guys agree that the total energy at point B ought to equal the total energy at point A? Good. Do I need to worry about the rotational kinetic energy of the ball?
I think yes.
Yeah.
If R is
I got the right answer.
whatever, it's just like effectively zero. Yeah. You even consider rolling?
Let's see. How is it worded? It says it's rolling smoothly. So despite the fact that the radius is very small, I think we still need to consider the rotational kinetic energy. Follow? All right. So here we go. So here's what I know is true. I know that the total energy at point A has got to equal the total energy at point B. What type of energy do I have at point A? GPE. That's got to equal, at point B, I've got GPE, KE, and RKE. So the GPE at point A is mgh. The GPE at point B is mg times 2 capital R, yes? KE at B is 1/2 m times v squared. Why am I happy? Because v squared just gives you gr, right? Plus our RKE. Tell me something useful about the RKE since it's smooth rolling. We don't even, oh, close, not I times KE. Beta times KE, right? So what is this thing? It's a solid brass ball. So what's beta for a solid sphere, you guys? 2/5, right? So this is 2/5, right? That's my beta times my KE. Everybody good?
Yeah.
Alrighty, so let's solve this mess. We're trying to solve for H, right? So, anybody notice anything useful? All of the MGs cancel. So I'm left with H equals 2R plus 1/2 R plus, what's half of 2/5? 1/5, right? 2/10.
Yes. Yes. My bad.
So your H ends up being 2.7 R. There you go. Oh, that's an R. So whatever 2.7 R is the answer.
If you got, so the answer is like 0.37 something, I think.
Well, I don't know. What's 2.7 times 0.14?
Oh wait, no, it was 0.378. So if you got 0.35, is that close enough, or do you think it's something?
That sounds to me like you might have neglected the RKE.
Okay. Oh, actually, I think I did.
What height did you get?
I got 0.35.
Yeah, so you got a lower than you should have. Yeah, so you ignored the RKE. All right. Notice, I didn't use any numbers in here. Gross and useful. All right. As much as possible, as we're getting closer to the AP test, I'd like to see you guys trying to do this. Okay? All right. Any questions with 29A? All right. B, if the ball is released from and then it gives you a height, what's the magnitude and direction of the horizontal force component acting on the ball at point Q? Do we want to run through that real fast?
Yeah.
Yep. Okay. So is everybody good with part A?
Yep.
All righty. I believe, well, we'll just start over. All right, so part B. So now we've got the same loop. We're going to start it from an initial position of 6R. And the question is, when it gets over here to point Q, we want to find out what the horizontal component of the force is. So I'm going to label that as Fx equals question mark. All right, so talk to me. Why does there have to be a horizontal force? That doesn't make sense to me. The ball is moving up. Why does there have to be a force to the left or to the right? Centripetal force, right? Oh, so that's what we're looking for. We're looking for the centripetal force, right? Okay. Sorry? Yeah. All right, so we're looking for centripetal force. So that's mv squared over r. No, it isn't. Over r. Right? So what do I need to find?
GPE velocity.
The velocity at point Q. And then we're pretty much done, right? Okay, so let's see. Up here, this is point A. This is already named point Q. The total energy at point A ought to equal the total energy at point Q. So the total energy at point A is GPE. So mg times 6r equals, what types of energy do we have at point Q? RKE, KE, and a little bit of GPE because we're still up by 1 radius, right? So mgr plus 1/2 mv squared plus 2/5 of 1/2 mv squared, right? Let me pause there for a minute. That's a lot to absorb. Did I lose anybody? All right, so can I make the same substitution I did before? Is my v still the square root of gr? No, because we're releasing it from a different point, right? Okay, in part A we said, what height would we have to release it from so that it just barely stays in contact? And we got a height of 2.7r, right?
Yes.
Now we're releasing it from a much higher height, 6r. Follow? Okay, cool. So we want to solve this thing for v, right? So let's simplify. Let's see, the m's all cancel out. Do the g's cancel again? They don't. Darn it. Okay, so I'm looking at 6gr equals gr plus 1/2 v squared plus 1/5 v squared. If you're keeping score, this is 7/10, so that's 0.7 v squared, right? Subtracting gr from both sides gives you 5gr. Good? So divide both sides by 7/10 is the same as multiplying by 10 over 7. So 50 over 7 is a number, all right? 7 1/7, so 7.14. Gr equals v squared, and then square root both sides, and you've got your velocity. I'm not going to square root it because we need to square it over here anyway. Cool? Any problems? Pretty good? Okay, so now we can find our centripetal force. It's the mass of the ball times velocity squared, 7.14 g r over r. The r's cancel. So there's your answer. So, and then your mass is like 0.000028 or something like that, and you know g, so. Cool, you guys? Alrighty. Any questions on 29? Okay.